Today we're going to start neural networks, the first section. So we're going to see how we derive from multiple layers of perceptron, and then later on multiple layers of logistic regression. We could build virtually any optimization problem and use neural networks to tackle those problems and get the best answer, coupled with the stochastic gradient descent that we already discussed in the previous session. So let's just start from some basics again. So on the left side, so actually on top right side here, you see that you've got two set of data, pluses and minus, and you had two x's, x1 and x2. So you saw that since this sort of data set was linearly separable, you could just distinguish that with your hypothesis, which was a set of weight you decide, and so we call them here H2, right? So on the middle figure, you had another way of using another hypothesis. It is called here H1. So you could distinguish and classify two different set of data sets here, pluses and minuses, with no issue. But on this figure, which is not, so it's non-linear separable, these two were. So simply by using any of these two alone, there's no way you can distinguish between these two set of data sets, right? If you use only H2 here, coming from the right figure, if you use H2, so you're going to classify one plus and one minus, but still you have another plus and minus on the other side. So you have virtually 50% error rate, which is completely random. If you use only your H1 classifier, you see that the same attributes happen to this as well. So you're going to have virtually 50% error rate. It's because this is a non-linearly separable data set, right? But gradually through the 50s, people understood that we can mimic the biological source of neural networks, which is what the brain functions, and add up all these smaller modules and stack them up to represent more complex representations and more complex classifiers. So you see, by combining H1 and H2 together, then you could be able to distinguish the pluses there and the minuses there. Something like this. Another way was, if you remember when we were talking about nonlinear transformations, we could find a circle function, or going to the higher polynomials. Like, I don't know, in this case we could have done it with only the second order of polynomial, but suppose you had a much more complex data set that requires you just to define something like this shape to distinguish the minuses and pluses, right? So this would require higher order of transformations, I would say. With the much more complex functions. But here we see that neural networks can simply add these very small and easy to understand, in this case perceptron, H1 and H2 together, and build a classifier that works actually. So if you go down, so this is the implementation of one layer classifier for this one. So you see that this was the x0, your artificial coordinate, which was 1. And those are input variables, your x1 and x2, right? So since this one was already above 1, so this was around and this weight comes from here. So you see that in order to distinguish between this, you need to, since it is already above 1.5, in order to make it classify both pluses and minuses, these two must be 1, or either of them must be 1. And this is the representation of perceptron for you. So if you add them together, here you're going to have the classifier, which represents and mimics an OR function. Because in OR, when you have variables like x1, x2, so this could be 0, this could be 0, this could be 1, 1, 1, 0, or 0, 1, right? And the output, let me just clear this. Well, I'm going to erase them all. Let's just cancel this out. So suppose this is the output of your OR. So it could be 1 if your x1 and x2 are either 1, right? This is 1, this could be 1, or one of them 1. If both were 0, the output would be 0, right? So x1, x2, each of them, if they are 1, so the output would be 1. On the other case, you could mimic an AND case, so that in order to make this one positive, because this is minus 1.5, both of them should be 1 to make it positive, right? And this mimics an AND case for us, because it requires both of the x1 and x2 to be 1. Okay? So you see that simply by using a simple perceptron, you could classify a nonlinear separable data set. So let's see if we can stack them up together and add more layers to represent more complex functions for us. I'm going to stop for a second here and then. Yeah.
Can you just repeat how you picked the 1.5?
It just one of the ways that you could choose in order to distinguish. But that should have been plus, that, and this one should have been minus. You could go further. All right. Now we see how we're going to stack up multi-layers of this perceptron that we just discussed. So suppose you want to represent that previous shape, and you wanted to present this H1 and H2 bar. So H2 bar is a negation of H2 actually. So this is the negative H2 or negation. So now we're going to see that in order to make either of these cases, so H1 positive, H2 negation, and the other case H1 negation and H2 positive. So because we don't know what they are, we can't make it with a perceptron, obviously. So what if we add another layer before these two, like here? First of all, to make these two, just like the previous slide, and then after we made these two, we use them in order to use in our classifier and mimics our function. And this is the intermediate layer that does that for us. So our artificial coordinates have both two values, 1.5, or it comes from there. So we are stacking them up together with these two perceptrons, and our H1 and H2, which were our two classifier, comes into play here with +1 and -1. So you see that by stacking up together, now we're going to build that function that previously we needed a circle or a higher order of polynomial in order to classify for us. All right? So now this one, in one case, this can represent H1 and H2 negation because this one comes in positive. And in one case, this one comes in negative here. And here we can build H1, H2, right? On the other case, we can build this one as well because -1 of H comes here and +1 of H2 comes here as well. So this represents our H1 negation and H2. And then the rest of the problem can be solved with another artificial coordinate that we input there. So this is called a two-layer perceptron. So now after this, people realize that we can stack up more layers, and by just using a linear classifier, a very simple one, like perceptron, we can almost classify many higher order of polynomial problems. And this is very useful to us. So let's see if we can go one step further and see how we can extend this to more complex data sets. All right. So now, if you, this is the final figure that we implemented. So it's as if you input two x's. So we call this layer input layer. And you simply, on top of the arrows, you put their weights. And here could be considered your hidden layers. And this is your output layer, right? In a very high level manner. So this three-layer feed forward, we call it feed forward because you feed all the information from left to right. You feed them forward into deeper layers of the network towards the output. So later on we see how backprop allows us to come backward, and that's what it's called, a backprop or backpropagation routine. So it comes from the output towards the input. But later on we're going to discuss about it. So now you see that by stacking them up, now we can classify that data set which was not linearly separable. Okay? All right. So now let's see how we could actually improve our classification if we have such a data set like this. So there's no way you can classify with any linear lines like with the classic perceptron. Definitely you need a circular function in order to mimic that. But say we can't afford to compute higher order of polynomials, right? We want to just stick to the perceptron and preferably maybe we can stack them up in multi-layers, right? So this is my target. What if I put 4 classifiers of perceptron here, like 1, 2, 3, and 4? You see, you're gonna define sort of a shape like this that is able to classify these points. In this case, they are doing well, right? But if you wanted to make a perfect circle, suppose you had some more data coming to this chunk of the figure, you would have missed them, right? So now we can even go higher. Let's add 4 more lines here as well and make them 8, which is this case. So we're gonna have 5, 6, 7, 8, 6. You see, now we can define with a higher accuracy. So using 8 perceptron, we could be able to mimic better. And this can go on and on and on. We can even put 16 perceptron. So you see that this very simple notion could be extended to very, very more complex problems just using that linear perceptron. But the only downside is how we're going to optimize it. Are we able to generalize the whole thing for every problems that we have? So these two were the early questions that in late 50s people wanted to find solutions for that. So later on they found that if they use a nonlinear function instead of perceptron, they can have a much better accuracy because it can mimic with a higher, say, with a soft threshold. So you remember we had logistic regression, so it was mimicking this for us. So we would call them a soft threshold instead of a linear threshold like this. So why not use that instead of perceptron for our classifiers? So with this we can generalize more, and we can put more realistic thresholds towards our classifier. On the other hand, how are we going to optimize this? How are we going to change how are we going to drive towards our local minima, right? So how are we going to apply a stochastic gradient descent here, which we already know? And this one was done by the algorithm called backprop that could be paired with a stochastic gradient descent. And later on we're going to discuss about this. So now we see that we have a roadmap, so we can generalize it, we can apply optimization there, and we can converge finally with the stochastic gradient descent. So let's see how that's going to work. Okay, we're done here. So another recap slide. So remember we had a binary case for our logistic regression. Our input weights were coming here. So those were our input. And on top we had the weights. Then our theta function, which was a sigmoid function from 0 to 1, would apply a soft threshold for us, and it would generate the probability, right? And when we say this is 1 given the x, no. So, and then maybe in the last session or two lectures ago, we started to talk about softmax function. that could address the case of multi-class logistic regression. And we saw it, and it was working like this. Just wait. So instead of only a binary class, we started to generalize it towards C classes, 1, 2, up to C. And then we saw that if we add a softmax classifier here, so this is softmax classification, and the input layer comes here, the inputs, these were the weights for each classes. So in this case, suppose we have like 3 classes. I mean, we could have more, stack them up here. Each of them were having their own signals, S1, S2, up to SC, and then the softmax classification would make sure that we compute the probabilities. This was the Yn class for us, the true class. Yn. True class. So we would compute its value of the signal, and we would divide it by the value of all the signals. So actually it would be a normalization. And then after that, we would pick the maximum number, right? If you remember. So now let's see how we're gonna extend this and use sigmoid in our multi-layer perceptron, right? So it's going to be a multi-layer of logistic regressions. Okay, so our signal S of I was the transpose the transpose vector of W I multiplied by X, and WI would be the weight of all the classes we had. So 0i, 1i up to the DI, right? And this would be the set of all the weights. We would call it small omega, and it represents our parameters for our model, right? So we would define the loss function for the x of n of I, and then we would calculate the loss function as E of n of omega equal to minus log of p hat I, and that was actually if you put all the values, you would have this divided by the summation of all, starting from I to all the classes you had. So if you remember, we had like, I was exemplifying, like suppose your S's, your SI's says would be like 120, 50, and 12. The result of this would be 120 divided by 120 plus 50 plus 12. Then you would have 50 divided by 120 plus 50 plus 12. And then here would be 12 divided by all of them again. So this would give us a normalized value, and the highest one would be the output of the softmax. Later on, we saw that when we have this, we can apply a stochastic gradient descent to converge and find the minimum, the local minimum, actually. So SGD was going like at iteration k, we would have all the parameters of k, which were W1 of k, W2 of k, up to WC of k, and we would update our Wj at k of I from the previous W of j of k minus the step size multiplied by the gradient we found using a loss function. And we would have to compute that value for the gradient, right? So now we're going to put them all together and see if we can stack these up in a multi-layer format and use a nonlinear classifier, or what we call it later on, activation functions. How are we going to build our neural network architecture? All right. Okay, so let's talk about a simple case. We have two-layer network with binary classification, right? So our input layer comes there with our artificial coordinate x0 equal to 1, and then we have x1 up to xd, d-dimensional space. So for each of them we have their w's, right? And then later on we can have sigmoid here as our soft threshold instead of perceptron, and this will give us some hypothesis that we can stack them up layer by layer to represent higher order of polynomial in order to classify more complex and nonlinear data set, right? So these two values are nonlinear functions. And it will help us to improve the accuracy by soft thresholding instead of putting hard threshold in a linear case. Yeah.
What is which changing from like H1 to V1?
So it could be other. Because we are trying to formalize them. We are trying to distinguish between them because we're gonna have more hidden layers in the middle. So we have to distinguish their value, right?
And what function is that also sigma?
No, this is called an activation function. Yeah. So later on, we're going to see that we don't actually use sigmoid in neural networks. We use hyperbolic functions because I'll describe it in a few slides. Okay, so this is going to be your input layer. This is going to be your hidden layers. It could be from 1 to n. In this case, we use sigmoid function. Here is an activation function. Could be any nonlinear function. And this is your output. Just a case of binary classification. Yeah.
So those are going to be different functions, right? The two nonlinear functions?
Yeah. So you see later in practice, people started to use many other nonlinear functions. But one of the most well-known one that we're going to discuss in this class is the hyperbolic tangent. So they call it tan h. Yeah, you're going to see it in a few slides. So the hyperbolic tangent. But recently, yeah, they have realized they can use other stuff like ReLU function. They can use other things. Yeah.
So is this better than logistic regression?
Yeah. So you'll see why it's better than logistic regression, because logistic regression doesn't have any. It ends here, right? After this, you're gonna have a softmax. But neural network, after that, you're gonna apply a nonlinear activation to that, so it's gonna soft threshold the output of that. Logistic regression is very helpful to give us certain probabilities, because the output of sigmoid, if you remember, the output of sigmoid was from 0 to 1, right? It was mimicking a probability. But in this case, the hyperbolic tangent that we're gonna see in a few slides gives us from -1 to 1. So it's a soft threshold for our weight. That's why we can stack them up into multi-layers. All right. So we have Wij, which is the weight on input vector I to hidden vector of j here. So I can define my hidden layers, h of j, as the function of theta that activates this Wi of j because they're coming from the input layer to this, right? Previous layers. For j from I up to n, just clear this out. And then my output would be well, actually this is my phi here. So this is wrong. I'll fix it later. This is going to be phi or phi. Yeah.
For the second line, should the first Wij be W0J? The expression for.
Oh, right. Are you talking about this one? Or this one?
That one.
Yeah, so it has the artificial coordinate as well inside. Okay, so this one also is phi. Yeah, you'll see the revised version when I upload it on the canvas. All right, so this is going to be your output. Here we mentioned with theta of 0. We could have mentioned it with phi. So yeah, I'll distinguish it later so that you won't get confused with your other sigmoid that you already knew. But just think about it as a nonlinear function. We call it the activation function here. So the common choice in our neural networks has been one of the hyperbolic function, the tangent hyperbolic or tan edge, which is this e to the, it's sort of close to our sigmoid, but instead of going from 0 to 1, it's going to go from -1 up to +1. And this is very helpful for us because it's going to apply a soft threshold throughout this span of data, because otherwise you would have to apply a hard threshold like this as a hard threshold. Or on the case of perceptron, your perceptron would have cut the line like this, right? This would be a perceptron. So you see that by applying a soft threshold such as the hyperbolic tangent, we can represent our data. The output of data would make much more sense for us, because on both extreme ends, if your signal is extreme going toward the either cases, it's going to go close to +1 or -1. If it's pretty close to 0, that would be close to your perceptron as well, because this was the case that these two lines are super close to each other. And it's going to be obviously much better than the hard threshold, because it would just make them +1 or -1 in either cases. So yeah, one of the properties is zero-centered, which is good for us. So the output of this would be equal to S if the S is on the extreme side of the graph. And on the saturation case, if S is pretty large, it's going to represent also for the both case of the function. And the other good point is, when you are dealing with derivations, the derivation is pretty easy to calculate. So it's going to be minus square of that, square of theta, or in this case, hyperbolic tangent of S. I need to stop right here. We're going to carry on next session. We'll see how we're going to stack some activation functions using this method and build a simple neural network to mimic our and OR, and finally coming up with XOR problem. Okay?